Bismillahirrahmanirrahim. Dear students, today we are going to discuss Julia-Olefination reaction, which is modified by Lithgow and Kocienski. This reaction is also basically for the formation of alkene from aldehydes using some another reagents, as we have discussed in the previous lectures for the olefination from aldehydes like Wittig reaction and etc. The key concepts of today's lecture is a brief introduction to Julia-Olefination reaction and also its modification. The detailed introduction to this olefication was given in the last lecture. Today we will discuss a brief introduction so that we can revise the some things about this lecture, and then the overall mechanism of the reaction will be discussed, and then the explanation of mechanism by step in detail. Also mechanism for the assay Julia modification and then Julia-Kocienski modification, and in the end we will discuss some synthetic applications of this olefination reaction. Julia-Olefination reaction. First in 1973, M. Julia and J. M. Paris worked on this and discovered this reaction in which sulfones are treated and converted into beta siloxy sulfones, and which are further reduced and elimination occurs to form alkenes. In 1978 and 1980, B. Lithgow and P.J. Kocienski modified it, and but this modification was not too much prominent. In 1985, 96, 98, 99, Kocienski further worked on this reaction, and many modifications were made, which also changed the path of the reaction and also affected the yield of the reaction, rate of the reaction. Sulfones are first converted into sulfonyl stabilized carbonyls, and these carbonyls are then reacted with carbonyl compounds to form alkene. The elimination step in the alkene is performed in different ways, and the modifications made in Julia-Olefication reaction differ in this step. First, the acylation followed by sodium mercury or samarium iodide reaction. The Julia-Lithgow olefination is termed in this modification, but the elimination by Smiles rearrangement is termed as Julia-Kocienski reaction. Both of these modifications are prominent in this reaction. So this Julia-Olefication reaction is also basically the conversion of aldehydes and ketones into alkene. The general reaction is shown here, in which you can see the sulfones are treated with base and aldehyde and acetic anhydride to form beta siloxy sulfones, and these are further reduced by sodium mercury in the presence of methanol to form alkene. This is the overall reaction mechanism of this olefination, that first sulfones are treated with alkyl lithium as a base, and we get carbanion. This carbanion is acting as a nucleophile, attacks on the carbonyl carbon of aldehyde or ketone, and we get an alk oxide ion. This alk oxide ion is treated with an acylating agent to get a good removing group, good leaving group. This reagent intermediate is treated with sodium mercury amalgam in the presence of ethanol, and through single electron transfer mechanism we get the alkene. This is the overall mechanism, and now we shall discuss each step of this mechanism in detail. The first step of this mechanism is deprotonation of sulfone. Deprotonation is here shown through n-butyl lithium. Here you can see the lithium is partial positive charge and butyl is partial negatively charged. The sigma electron between these two are moved toward butyl, and then butyl, acting as a nucleophile, attacks on the hydrogen of sulfone. This thing also is the in this can be explained this way, that Bu negative whole with full negative charge as a nucleophile is not created here, but the sigma electron present between lithium and butyl act as a nucleophile through butyl group, which attacks on the hydrogen, and we get butane. The sigma electron moves towards the carbon and sulfur bond, and there is a double bond creation, and then simultaneously the S double bond O is broken, and pi bond is broken, and oxygen gets the negative charge. This negative charge containing intermediate is too much stable due to resonance. Here you can see the three resonating structure. This negative charge is moving towards the sulfur, and the second oxygen gets the negative charge, then that moves back, and then the carbon gets the negative charge, and you can see that this anion intermediate is resonance stabilized. Here is the question. First question is that why the proton of methylene is so acidic. As the answer is due to electron withdrawing group, because S double bond O sulfonyl group is too much stronger group, electron withdrawing group, and due to this strong electron withdrawing group, the neighboring carbon gets too much partial charge, negative charge, and the hydrogen gets the partial positive charge, and it becomes too much acidic. The second question, why this anion is called sulfonyl stabilized carbon ion. This anion is called sulfonyl stabilized carbon ion, as you have seen that this creating anion is the resonating structures of three different types. So therefore it is stabilized by the resonance, and sulfonyl stabilized because sulfonyl group is much involved in this stabilization process. Here is the second step of this reaction, which is reaction with aldehyde. The sulfonyl stabilized carbon ion, which was produced in the first step, is now reacted with aldehyde. The sulfonyl stabilized carbon ion acts as a nucleophile, and it acts as a nucleophile through the carbon. You can see the negative charge oxygen moves towards the sulfur, and double bond moves on to the carbon. Carbon, acting as a nucleophile, attacks on the carbon of electrophilic center of carbonyl of aldehyde, and then the pi bond is broken and oxygen gets the negative charge, and we get this alkoxide ion. The negative charge alkoxide ion is stabilized, counterbalanced by the positively charged lithium ion. This sulfonyl stabilized carbon is a strong nucleophile, so it can easily react with the carbon of aldehyde, and it convert it into product into this intermediate. Here is the question, why the attack on carbonyl carbon is through carbon of the sulfonyl stabilized carbon, not through its oxygen. Answer is written as the size of the carbon is smaller than that of oxygen. You can compare the sizes of oxygen and carbon, and you know that carbon is smaller. You can see here the size of carbon is greater as compared to that of oxygen. As you know, carbon is atomic number 6, oxygen has atomic number of 8, and in the same, both are in the same period. The size of carbon is greater as compared to that of oxygen, and therefore the carbon will act as a strong nucleophile due to larger size. So the priority of this anion is to attack as a nucleophile through the carbon instead of oxygen. So therefore the attack is through carbon and not through oxygen. And you can see the oxygen is competing with the other oxygen also, so this thing also diminishes the chances of the attack from the oxygen. Here is the third step of this reaction, that acylation of intermediate with acetic anhydride is the mechanism for the acetylation through acetic anhydride is shown here, and as we discussed earlier, the acylation is required to convert the alkoxide ion into a stable good leaving group. Here you can see the negative charge of alkoxide ion acting as a nucleophile attacks on the carbonyl carbon of this anhydride, and pi bond is broken, oxygen gets the negative charge, and this next step, this oxygen negative charge moves towards the carbon and making again double bond, and the carbon oxygen sigma bond is broken and oxygen gets the negative charge, producing the acetate ion. This acetate ion is counterbalanced by the lithium cation, and we get the lithium salt of acetate ion, and an intermediate compound which contains acetyloxy group at the beta position of the sulfone. Here you can see that this is the sulfone group, and the nearly alpha carbon and then beta carbon is attached with the acetyloxy group. Acylation is preferred to convert the alk oxide intermediate into a stable intermediate with good leaving group, as this acetyloxy group is a good leaving group. When it will be left, it will be converted into acetate ion, which is resonance stabilized and will be easily captured by the medium. Here is a question: what will be the more active, acetyl chloride or acetic anhydride, or which thing we will prefer to react with? If we see the preference for the choice of reactivity, then the scientists choose acetic anhydride instead of acetyl chloride. Although the reactivity of acetyl chloride is higher, is greater, and the reaction is faster as compared to acetic anhydride, but the acetic anhydride is less expensive, number one, and number two, it's is less dangerous as compared to that of acetyl chloride. Here the byproduct is acetic acid or acetic acetate ion, which is less acidic, less toxic as compared to that of acetyl chloride. In that case, the leaving group is chloride ion, which will be yielded as HCl and so on, and this is a dangerous byproduct as compared to acetic acid. Also, you can you see that the Cl minus is not a good base, but the acetate ion is a good base. So all these things make this the use of acetic anhydride prominent for its less expensiveness and less toxicity. The fourth and last step is the olefin formation step through SET. SET means single electron transfer mechanism. As you know, radicals are produced in different reactions by different ways. Number one, through homolytic cleavage. You know, homolytic cleavage means that the sigma bond is broken in such a way that each combining atoms takes away its electron and the bond is broken. Second is the flow pre-existing radical to another position. That is, a radical is already present in the chain, as we know in the polymerization of alkene through free radical mechanism. The radical moves along the chain from one position to other position and propagates the chain. The third way to produce radical is single electron transfer. Single, as you can understand by this word, single electron transfer means the transferring of one electron from one species to the other species. The electron rich species give the electron to the electron poor species. The electron rich species, which is the giver of electron, becomes positively charged, that is it becomes radical cation, and the receiver which is gaining the electron becomes negatively charged, and it is called radical anion. Here you can see the example that R and R prime are electron combined in such a way that one electron is moved from R to R prime, and R gets a radical and positive charge, and R prime gets a radical with negative charge. So these are called radical cation and radical anion. Alkali metals, that is group 1 metals, are the famous for this kind of chemistry, and most of them mostly lithium, potassium, sodium are used from this group for this purpose. Here if M is for the metal of first group, and you know that they have one valence electron, one electron in the valence shell. This one electron is given to the second member, and this metal gets the positive charge with no odd number of or unpaired electron. That is, it is only a cation, not a radical. But R, the second group gets an electron, it becomes a radical with a negative charge, and that is called radical anion. Here is an example to explain this thing more clearly, that sodium acts or reacts with methyl acetate in such a way that it gives one electron to the carbon of carbonyl group, and the pi bond is broken and oxygen gets the negative charge. Now the carbon has odd number of electrons. Similarly, the second molecule also has this. Both of these electron can bond with each other to form a single sigma bond, and we can get a dimer of these two species. So this is the basic theme of the single electron transfer transfer reaction, and in next slide we discuss our reaction, which is involving this single electron transfer mechanism. This is the mechanism for single electron transfer for our reaction, that the sodium metal reacts with methanol, forming an alkoxide ion. This alkoxide ion takes away a proton from the intermediate which was synthesized in the last step, and the two electron of sigma bond moves towards the carbon-carbon sigma bond and makes it double bond, and the acetyloxy group moves away as a leaving group. In the next step, this alkene is treated with sodium metal in such a way that one electron of sodium is transferred to the one electron of sulfur. Here you can see the arrow that the two electron pi bond between sulfur and oxygen is broken, and one electron moves towards the sodium for the formation of bond there, and one electron moves to the sulfur, and in next step you see that sulfur contains an odd number of electrons, that it becomes a radical, and the oxygen gets a negative charge because it gains one electron from the sodium, so it gets a negative charge and sodium gets positive charge, and we get a salt in which sulfur has a odd number of electron or a radical. And in the next step, the sigma electron present between sulfur and carbon or moves in such a way that sulfur takes its own electron back and it gets a neutral molecule, and the carbon of the alkene gets its odd number of electron in the form of free radical. Another sodium metal comes and gives one electron, odd electron, to this carbon, and carbon becomes negatively charged and sodium becomes positively charged. This negative charge moves in such a way that the hydrogen of this alkene, or you can say this negative charge moves or attacks on the methanol molecule, from which it obstructs one proton towards itself, and it gets the hydrogen on this. With we get an alkene on which two R groups and two hydrogens are present, and the methanol molecule is converted into methoxide. This negatively charged oxygen is balanced by the sodium ion, which was produced in the last step. I mean here in this slide here sodium radical is converted into sodium ion at the second step. This sodium ion is counterbalancing this methoxide ion. If we see the stereochemistry of this reaction, stereochemistry alkene is independent of the stereochemistry of the sulfone intermediates. That is the sulfone intermediate stereochemistry has no effect on the stereochemistry of the alkene. The reason is that the cis and trans vinyl radicals, as you have seen here, can equilibrate, and the trans radical is more thermodynamically stable of the two, so it is formed in major proportion or mostly. Both diastereomeric acetoxy sulfones led selectively to the same product, that is E-alkane. Here you can see again the cis free radical and then the trans radical, but as they are they can equilibrate with each other, and the trans product is more thermodynamically stable, so it is formed in major proportion, and we get the product according to its configuration, and it is mostly E-alkene. Here is the first modification of Julia Olefination, that Sylvester-Julia Olefination. This Sylvester-Julia is another scientist. The first reaction which we have discussed was also named after the Julia, called Julia Olefination, and this reaction modification is also by the same named scientist, but the suffix is different, that is Sylvester-Julia Olefination. It is another scientist. This is a modification of the classical Julia Olefination reaction, that is the replacement of phenyl sulfones with heteroaryl sulfones. The basic difference between these two reactions is that in case of classical Julia we used simple phenyl sulfones, but in this Sylvester-Julia Olefination reaction here we use heteroaryl sulfones, and due to this heterocyclic aryl sulfone, the pathway of the reaction is changed dramatically. First, benzothiazole sulfone was used and treated with lithium diisopropylamide as a base, which created its carbon ion, which reacted with aldehyde or ketone to form an alkoxide ion. Unlike the phenyl sulfones, because in case of phenyl sulfone the alkoxide ion was treated with acetic anhydride to make it good leaving group, and then it was treated with sodium or sodium mercury amalgam through single electron transfer mechanism, and we get the alkene. But here this intermediate two undergo Smyle's rearrangement, and we get sulfinate salt. That is two steps have been eliminated from the last mechanism, and we get the product. This sulfinate salt products, a mixture of E and Z alkenes are obtained. The reality is this for this variation of E and Z alkenes, that benzothiazole variation does not involve equilibrating intermediates. So stereochemical outcome is a result of the stereochemistry of initial carbonyl addition. If that was cis addition or E addition, then we get the E alkene product. If it was Z, then we get the Z alkene product. This is the reaction of Sylvester-Julia olefination. The first heterocyclic sulfone is treated with LDA and as a base and carbonyl, and we get this intermediate alkoxidine. And here you can see the reaction or movement of this alkoxidine. There's O minus attacks on the this carbon, double bonded carbon, and the pi bond is broken and nitrogen gets the negative charge. In the next step, the negative charge of nitrogen moves back and the carbon sulfonyl bond is broken, and sulfur oxygen of sulfonyl gets the negative charge. And this rearranges in such a way that can be cis, that can be trans. And then the negative charge of sulfonyl moves back towards the sulfur, and the sulfur C sulfur bond is broken, and we get the SO2 molecule as a byproduct. This C2 electrons moves towards the carbon single bond, and we get a double bond here. And then the oxygen CO bond also is broken, 2 electron moves toward the oxygen, and we get the oxide, heterocyclic oxide ion, which is counterbalanced with the lithium as a salt, and we get the alkene. And this alkene is a mixture of E and Z alkenes. Second modification is the Julia-Kocienski Olefination reaction. This Julia is the same scientist which we have discussed in the last slide, that is Sylvester Julia, and Kocienski is another scientist which modified its reaction only through the change of the heterocyclic group present in the sulfone. But the thing for this Julia-Kocienski olefination reaction, which is different from the last Sylvester-Julia olefination, is that it has good E selectivity, that the product is good in E alkene, but the last Sylvester-Julia reaction gives the mixture of E and Z alkene. This reaction Julia-Kocienski olefination used alkylating agent as tetrazole, which was present in the sulfone group. This the high E selectivity. The remaining mechanism is the same as we have discussed for the benzothiazole sulfone. This tetrazole also followed the same mechanism. The only difference is that this heterocyclic reagent gives the E selectivity. The high E selectivity can be explained in such a way that it is kinetically controlled diastereoselective addition of metallated tetrazole sulfone to non-conjugated aldehyde, and so it yielded anti-beta alkoxysulfones, okay, which stereospecifically decompose to E alkene instead of Z alkene. If we change this tetrazole with tertiary butyl tetrazolyl methyl sulfone, then the reaction conditions are either sodium bis trimethylsilylamide at -70° C in tetrahydrofuran, or cesium carbonate tetrahydrofuran at +70° C. So only the conditions vary, remaining points are the same, that it is also E selective. This is the general reaction for Julia-Kocienski olefination, that tetrazole sulfone is treated with carbonyl in the presence of base. Here is the potassium salt, and we get the alkene, and this thing was also repeated with tertiary butyl with the ketone, and using cesium carbonate as we have discussed in the last slide, or sodium amide, and we get the alkene with E selectivity. Here is given some experimental procedure for this Julia-Kocienski olefination. This is to explain that there was a question. Both of the sulfone have acetic proton that we omit through the use of a base, and aldehydes or ketones also have acidic proton if they have a beta proton at their alpha position, alpha carbon. So when both of them have acidic proton, then why only deprotonation occurs in sulfones? if this question arises, then this procedure will explain this thing, that first inert atmosphere we get sulfone in the solvent and uses the base which deprotonates it. That is, we have not filled or added the aldehyde. We have taken only sulfone having acidic proton, and the base is treated with it, so that we get the carbon ion. Then in the next step, after stirring up some time, then in the aldehyde is added, and this aldehyde will act as an electrophilic center, and the already present carbon ion will act as a nucleophile, and the reaction will proceed. Here is some synthetic applications of this reaction. First is the synthesis of Pterostilbene, which is used as an anti-diabetic drug, and this is prepared through the reaction of a sulfone with an aldehyde, aromatic aldehyde. In the conditions which we have discussed, it uses the base of potassium carbonate in methanol, and we get the drug of anti-diabetic drug. Second is the synthesis of precursor for Acylation, which is used in antibiotic. This the region, the compound shown here is the precursor, which is further converted into this drug after reactions of some steps. Here you can see also, first is the sulfone shown with having alpha hydrogen, and is treated with an aldehyde, and we get a double bond. The aldehyde already contain a double bond, and we get another double bond, so conjugation is created here. Here is another drug, Bryostatin, which is used in Alzheimer's disease. Alzheimer's disease related to brain acetylcholine, etc. And here you can see the reaction of first the reagent you are seeing reacts with the second reagent having sulfone, and both of them are treated in the presence of a base and tetrahydrofuran, and we get the product intermediate, this which is converted into the final drug after too many steps. Next drug is anti-cancer and antimicrobial drug, bengamide E, and here you can see the sulfone having alpha hydrogen is treated with an aldehyde. Pharmal group is present here in the presence of base, and DME is a solvent. My temperature minus 78 degrees C at 2 room temperature. 2 room temperature means first that we use the region at minus 78, then slowly the temperature is moved to the room temperature. The percentage is 62%, and we get the intermediate, which is further treated with many steps, and we get the final product of anti-cancer antimicrobial drug. Next drug is anti-tumor, Herboxidiene, and this drug is also prepared after too many steps, and we are discussing here only simple steps which are involved and are related to our this reaction. First here is the aldehyde is treated with a tetrazole sulfone and in the presence of a base, and we get a double bond alkene, and this alkene is treated with too many steps, and we get a final product which is also contains an aldehyde group, and this aldehyde group is further treated with heterocyclic sulfone, which converted into an alkene, and we get a conjugated double bond. This you can see the red colored yields. First step 93% yield, and the second step is also 81% yield. So the yield of this reaction, actually Julia-Kocienski reaction, is very good. Here is another antibiotic drug, Indolizomycin, which uses this reaction during its synthesis. First step, you can see there is an aldehyde group at the bottom of the molecule, which is treated with a sulfone and alkene sulfone, already bearing a double bond, and after the reaction of both we get this acyloxy intermediate, and then it is converted in the presence of sodium mercury and methanol into alkene, and we get a conjugated system of the alkenes. And this conjugate system of alkenes then moved through a number of steps, and finally we get the product of this drug, which is used as an antibiotic drug. Acylation is also another drug molecule which has anti-fungal activity and anti-tumor activity, and here you can see the PT sulfone is used for the synthesis of this drug, which is treated with a formyl group, aldehyde group, which contains alpha beta double bond, that is alpha beta unsaturated aldehyde, and this double bond is in Z isomer, which is moved towards the intermediate and then towards the final production of alkene with the E isomer of the alkene, and then after further steps this molecule is converted into the final drug compound, that is Acylation. Here you can compare the reaction of this drug through the yield using different bases, different solvents, different temperatures. The drug is antifungal Ambruticin, and here you can see the aldehyde group is treated with sulfone, and we get the alkene product. Here you can see the metals use sodium, potassium, lithium, and the solvent is tetrahydrofuran, DMF, DME, and also mixer DME and cronether, THF and HMPA. So DMF and HMPA. Temperature is minus 78 degrees C, minus 35, 60, 35, minus 35, and the ratio you can see here that E ratio Z is 1:8, 1:6, 1:1, 1:3, 3:1 in case of this lithium, and 31, greater than 31 and greater than 31 if we use the DMF and HMPA. So there is a great involvement of the nature of the solvent, nature of the temperature, and nature of the base in the your product ratio or product selectivity or specificity. So it should be kept in mind while taking these reactions, that which base should be used, which solvent should be used, and which temperature should be maintained for the reaction, so that we can get our desired product up to maximum yield. This is the anti-cancer drug Okadaic acids. I think there are too many examples have been given, so this is the last one for this reaction. And here you can see the sulfone having alpha hydrogen, and on the other hand there is aldehyde, both are treated, and we get the double bond between these two species, and the resulting drug is used as an anti-cancer agent. So all of these examples are only to show you the importance of this reaction, the different conditions of this reaction in which this reaction can be performed, and the conditions which can be varied by the different actually all these examples are the work of different scientists which they have performed with different conditions with specific results, and I am not mentioning here the references of those research papers, but only to see you, to make you to realize you that what is the going on for these reactions, and the conditions, the nature of conditions, what is the role of conditions, and other things also. So this is the all about of today's lecture, and thanks.